In computer science, a real common task is to find the largest value or the smallest value in a list of numbers. It can also occur when you want to alphabetize strings. As it turns out, there's a simple algorithm that will help you do just that. I call it the King of the Mountain algorithm, and I first experienced it way back in elementary school. So let's go back in time. My favorite subject in elementary school was recess. We would run outside to release the stress of cramming all that valuable learning into our developing brains. Outside, there was a concrete bench, and we used it to play a game called King of the Mountain. One kid would jump up on the bench, that is, the mountain, and be king, and the others would take turns trying to replace him by pushing him off the bench. I was pretty scrawny, but I could run fast, so I often beat my classmates to the bench. Here I am at recess, headed toward that prized mountain. As the first one to reach the mountain, I was the first king by virtue of no competition up to that point. For a very short time, then I was the current king. My reign wouldn't last very long because somebody else would soon reach the mountain. In this animation, the next person to show up was Tara. And let me tell you something, Tara was tough. As soon as she jumped up on the bench, my time as king was done. This meant that Tara was the new king and also the current king. Keep that last sentence in mind. As for me, now I had no title at all. But Tara had to face challengers also. The next person to come along was Jose, and he stormed up the mountain for his attempt to be king. No such luck. Jose met the same fate that I did, and Tara remained the current king. I told you, Tara was tough. But notice I said that Tara remained the current king, not that she was the new king. The only time you could get a new king is if someone beat the current king. Keep that in mind. Next was Billy. Billy probably started lifting weights when he was about 3, so he was even stronger than Tara. In their battle, Tara lost, and Billy became the new king, and also the current king. Now, in this story, you could always tell who the current king was by who stood alone on the bench. So in that sense, the bench was what kept track of the current king. Now, we can envision a line of kids still wanting to compete to be king. And on the other side, we have kids who've already been beaten in battle. It's important for you to see that no one in the line on the right will ever compete against anyone in the group on the left. Because by logic, the current king has beaten everybody in the group on the left, either directly or indirectly. Coming back to the present time, the King of the Mountain algorithm has 2 parts. The first part says, the first one in line becomes the first king and also the current king. The first one in line didn't have to compete against anybody in order to become the first king. The second part tells us that everyone else in line is going to compete against whoever is the current king when they get their turn. It doesn't matter how many kings, if any, came before this current king. It only matters who the current king is. And this second part keeps repeating as long as there are people in line waiting to compete. Notice that the current king may be replaced by the next person in line or never be replaced at all. Let's look at some actual code that uses the King of the Mountain algorithm. We're going to define 5 integers shown here. Then we'll get the user's values for the first 4 integers. To save space, I'm not showing that code. So let's suppose the user entered 14, 6, 18, and 19. Here's part 1 of the algorithm. The biggest variable equals N1 because N1 is the first variable in line. That means biggest now equals 14. You can think of biggest as the bench in my story. That is, it keeps track of the current king. And right now, the current king is 14. Now we'll check to see if N2 is larger than the current king. In other words, the variable we named biggest. The answer is no. 6 is not larger than 14, so the current king is still 14. We'll do the same sort of thing to check to see if N3 is larger than the current king. This time, the if statement is true because 18 is larger than 14. So 18 becomes the new king, which makes 18 the current king stored in the biggest variable. Finally, let's check to see if N4 is larger than the current king. Since 19 is larger than 18, the if statement is true, and the 18 stored in biggest gets replaced by the 19 in N4. When these lines of code execute, the biggest variable is going to contain the final current king, which will be the largest value. Now you might be saying, oh yeah, that works because the largest one was the last variable to be checked. Let's look at an example where that's not the case. This time, let's assume that the user entered 30, 29, -4, and 20. In other words, the N1 variable contains the largest value of these four. Once again, the value of N1 is copied into biggest, which means that 30 is the first king and also the current king. When we check to see if N2 is larger than the biggest variable, the answer is no. So N2 falls by the wayside. Same sort of thing happens when we compare N3 to the biggest variable. No contest there either. Likewise, the 20 stored in the N4 variable is not larger than the 30 stored in biggest. So here's a situation where the original king remained the king because no other values were larger. So there it is, the king of the mountain algorithm. It's going to work for integers, floats, doubles, characters, and with just a little bit of tinkering with strings. You're going to run into situations where you can use it fairly often in your programming experience. I do have a question for you. What would have to change in the algorithm to find the smallest value?